It is my pleasure to introduce Peter Kagey from USC, and he'll be talking about generalized spinning switches. So, Peter, take it away.
Cool. Thanks, Josh. Okay, so this talk is gonna be about this generalization of this puzzle that my understanding is first showed up in a Martin Gardner column, but kind of got immortalized or popularized in this puzzle book by Peter Winkler, Mathematical Puzzles: A Connoisseur's Collection. They, like a lot of puzzles, you sort of have to think about it for a minute in order to really know what's asking. So I want to spend a good chunk of the beginning of this talk trying to make sure that sort of everyone who's watching has some intuition for what's going on before I start generalizing it. Otherwise, I think it won't feel very motivated. So here's the problem, copy and pasted from the book. Okay, so we have these 4 identical switches. The switches, you can't tell whether they're on or off. They're like buttons. You press it, and by looking at it, you can't tell whether it's on or off. And they're wired in series to a light bulb, which means for the light bulb to be on, all of the switches have to be on. And the puzzle is going to work via a series of turns. So it's sort of a 2-player game. So player 1, who's trying to turn on the light bulb, is gonna press some subset of switches. If the light bulb turns on, the light bulb sort of initially is turned off. If the light bulb turns on, then that player is won. Otherwise, the adversary is gonna take the switches, which are on like a lazy Susan, they're on a rotating table, and they're gonna spin the table. So you sort of you can kind of keep track of the relative order that the buttons were pushed in, but you sort of lose track of which button was which. Okay, and the miracle of this puzzle is that there's a deterministic algorithm that you can press the buttons in a series of orders. So, you press all of the buttons and then the adversary spins the table, and you press, the left bottom button or whatever it is, some algorithm, and you can turn on the light bulb. So in the spirit of trying to build intuition as quickly as we can, this is a little bit of a tricky puzzle. I'm gonna start with a slightly easier problem. Okay, so the easier problem, it's the same puzzle, except for now, instead of having 4 switches on a square table, we're just gonna have 2 switches on a rectangular table. Okay, and so what's our strategy here? How are we gonna try and turn on the light bulb? So first off, we assume that the light bulb isn't already turned on, otherwise we've won. So we're gonna assume that the light bulb is turned off. And moreover, we're gonna assume that both of the switches are in the same state, which since the light bulb is turned off, that means both of the switches are turned off, okay? And what we're gonna do as our first step is we're gonna flip both of them. If they were both turned off, if we're right about our assumption, they're both turned off. If we flip both of the switches, now they're both turned on. Okay, and so the light bulb turns on. But if the light bulb doesn't turn on, that means that we were wrong about this assumption that they were both turned off to begin with. So they weren't both turned off to begin with, and they weren't both turned on to begin with. We know that because the light bulb is off. So that means one was turned on and one was turned off. So if the light bulb's still not on, what we do is we're gonna flip one of the switches. And if we get lucky, the light bulb turns on. Otherwise, we've gone from we've turned off the switch that was already on, so they're both turned off. And so we can go back up to the beginning. Now we can correctly, if the light bulb still isn't on, we can correctly assume that both of the switches are turned off. And if we flip both again, the light bulb turns on. So the strategy here is we flip both, we flip one, we flip both, and that's gonna turn on the light bulb. Okay. And now what we're gonna try and do is we're gonna try and do somehow a spiritually similar idea on the square. And then in this talk, we're going to try and generalize this. We're going to have different kinds of shapes, different kinds of switches, etc. Okay, but before we do, you would think that in the stepping stone from going from the 2-switch problem that I've drawn here to the 4-switch problem that we started with, it would make sense to step through the 3-switch problem, the triangular problem. The catch, which is maybe a little bit surprising or maybe not, is that for the 3-switch version of this, where we have our switches on the corners of a triangle, there's no strategy that can deterministically turn on the light bulb. Basically, what can happen is if we have two switches that are the same and one switch that's different, there's sort of no way to guess the one switch that's different, right? So maybe we would, maybe we'd hit this switch and this switch, but we could sort of happen to always get unlucky, right? Or maybe we just try and match the one switch that's off, and we sort of always have a 1 in 3 chance of guessing it. So there's no way to deterministically get out of the two are the same and one is different state. Okay, we're going to go back to that about how there's no strategy for some of these setups, but let's talk about the strategy for the switch on the table here. Okay, so we're going to do the same thing for the square table that we did for that rectangular table with 2 switches, which is we're first going to assume that they're all in the same state. And if the light bulb isn't turned on, so let's turn this off. If the light bulb isn't turned on, then we know that, and we're assuming they're all in the same state, that means they all have to be turned off. So our first step that we're going to do is we're going to switch all of the bulbs. And if our assumption was right, that they were all turned off, well, now our light bulb turns on, so we're done. But if our assumption was wrong, they weren't all turned off, then we know that it's in some other state. They're not all the same. So what we're going to do is assume next, once we've tried that, we're going to assume, okay, if they're not all the same, well, let's assume that the diagonals are the same. Let's sort of just guess that the diagonals are the same. And if the diagonals are the same, then what we can do is we can toggle the diagonals. So whoops, we just are going to just choose 2 of the diagonals. It doesn't matter which 2. And if the diagonals are the same, then toggling the diagonals is going to put us into the other state. So like if we had chosen these 2 diagonals, then all of the switches would be off. And if we chose these 2 diagonals, all of the switches would be on. But what matters is that they're all the same. Okay, so first what we're going to do is we're going to start off and we're going to assume they're all the same. And if they're not all the same, we're going to assume that the diagonals are the same. So we're going to flip the diagonals. And if that assumption was right, that the diagonals were the same, now switching the diagonals makes them all the same. Okay, so now we're going to go back to here. Okay, and so if either of these 2 assumptions were correct, then flipping all of them and then flipping the diagonals and then flipping all of them is going to turn on the light bulb. If the light bulb still isn't on, we know these 2 assumptions aren't the same. So we're going to kind of rinse and repeat here. So we're going to assume now that there's an even number of them on. And if there's an even number of them on, then we actually know that it's going to, okay, they're either all the same or they're diagonals or there's 2 to the side, 2 to a side. So we're going to do this 2 to the side switch, which is either going to make them all the same or all diagonals. So what we'll do here is we're going to swap these over. And now we know once we've chosen 2 that are on the same side, well, we know we're in one of these 2 states, but we know how to solve the puzzle if we know we're in one of these 2 states, which is that we do this thing. Okay. And then when I'm at this point, I always am hungry because it reminds me of carne asada. So that's how I can remember. The reason for these letters is A is for all, D is for diagonals, S is for side. And if none of these are true, this means an odd number of the switches are on. And so what we're going to do to get out of that state is we're just gonna flip over one of the switches. Okay, so if we've gotten to this point, the light bulb still isn't on. That means that to begin with, we had one switch. We had, sorry, an odd number of switches that were on. So if we just toggle any of them, now we have an even number that are on. And so we toggle that one. We know now we are in these first 3 states, 1, 2, or 3. And we know how to get out of that. Okay, so this 15-step strategy, all diagonal, all side, all diagonal, all 1, all diagonal, all side, all diagonal, all, will turn on the light bulb at some point in this process. So we can deterministically turn on the light bulb. Okay, so I've spent half of my time sort of explaining the puzzle, and I'm going to try and spend the other half of my time, or roughly other half of my time, sort of talking about some generalizations here. Okay, so this problem came up at the Graduate Student Combinatorics Conference in 2019. We were talking about this puzzle, and we came up, after sort of a few days of discussing this on breaks, we came up with this strategy. If we have these 2-way switches, there exists a strategy on an n-gon. So remember, we do have one on this sort of 2-gon. We don't have one on this triangle. We do have one on this 4-gon on this square. There exists a strategy on an n-gon if and only if n is a power of 2. Okay, so we can have a strategy on these 2-gons, on these squares, on octagons, on 16-gons, on 1024-gons, you name it. But we actually can't, we don't have any strategy on anything else. Okay, so what that means is, like I showed before, there isn't a switching strategy on the triangle with these ordinary two-way switches. But it turns out that if we have different kinds of switches, so if we have a 3-way switch, so maybe we think of these switches as behaving like a cyclic group mod, of 3 elements, then there is a switching strategy on the triangle with these 3-way switches. Okay, and it's going to go similarly. I'm going to go a lot faster here. We're going to assume that it's all the same. If it is all of the same, then we're just going to toggle through all the different possible cases that it could be. If that's wrong, we're going to assume that they're all different. And how we're going to do that is like this. Okay, and then if the light bulb still isn't on, we're going to assume that 2 are the same and 1 is different. And this is I'm kind of being magical about this. I'm not really explaining how this works, but all right, we're going to put another C in here. It turns out that if we do this 26 move strategy, then we're gonna turn on the light bulb with these 3-way switches. Okay, so we couldn't turn on the light bulb with 2-way switches on a triangle, but we can with these 3-way switches. Okay, so what's the more general context? So like, how do we make this a math problem? So the more general context is that we sort of have 2 kinds of groups that we're working with here. First, in our main example, we have these switches which are behaving like a group. They're behaving like the integers mod 2, right? The switches are either on or off. Or in the last thing that we saw, they're behaving like the integers mod 3. They're behaving like a cyclic group. And then we also have this spinning table. And this spinning table, if we have an n-gonal table, is going to behave like this, the cyclic group with n elements. Okay. And I'm sort of purposefully using these 2 different notations to refer to these cyclic groups, just so that we can keep things straight. Okay, so the switches we're going to think of as behaving like the integers, mod 2, and or maybe some other group, and the table is going to behave like a cyclic group. Okay, and now how do we encapsulate this idea? So we're gonna basically model this problem as a Reith product. Okay. And if you know what a Reith product is, that's great. If you don't know what a Reith product is, I mean, a Reith product is, at least in this context, is kind of this puzzle, okay? So a Reith product is that we have this group that the switches behave like, so the integers mod 2, and we have this group T, which is what the table behaves like, so this is the cyclic group on 4 elements. And the Reith product sort of formally is we take k copies of our switches, okay? So here in this drawing, k is equal to 4 because we have these 4 switches, and we do this semi-direct product, okay? Sort of whatever that means. And this group is just pairs of basically ways of picking the switches that we're gonna press. So that's sort of one part of the group. And then the way that we're going to spin the table T. Okay, so this is how we can think of the Reith product here. Okay, so we have this now. We have this machinery. We have this way to describe, this sort of standard way to describe the symmetries of this puzzle. Okay, so here, this is sort of what I've been talking about. We can think of this puzzle as being the integers mod 2, the Reith product of the integers mod 2 with C4, and on this triangular one, we have these 3-way switches, and then the symmetry, sort of rotating the triangle. Okay, and so now how do we sort of formalize this? What we're going to do is we're going to say that a switching strategy is, okay, so I'm going to wrap it up here, but the idea here is that a switching strategy is a sequence of switches. So you say like what your switches are going to be, such that given any sequence of these table spins, that if we look at the partial product, we eventually hit every possible state in S to the K. So so this gives us a nice formal way that now we can start using sort of some of our group theory or abstract algebra theorems to talk about under what parameters we have strategies to solve these puzzles. Okay, cool. Well, I'll leave it here so that we have a couple minutes for questions. So does anyone have any questions?
So before we get into questions, let's just take a moment to thank Peter for his interesting talk. And yeah, you can unmute yourselves and clap or just use the applause react. So we have 3.5 minutes left. Are there any questions from the audience? You can either unmute yourselves and ask or put a question in the chat.
So I've got a question. So
Sure.
You've said that if you have a two-way switch and you have a table with 3 switches, you do not have a strategy. Is there a way you can sort of get that by looking at the Reith product of Z mod 2Z and C3?
Yeah, that's a good question. So so the way that I know how to show that is by basically making like it's a formal argument, but it's basically this heuristic argument, which is that you can sort of get stuck in these states. Though we can use this Reith product structure to say some other things. So let me scroll down here and sort of say, so I have this theorem here, which says that if we have an example of a Reith product that doesn't have a switching strategy, then we can come up with other examples that don't have switching strategies. So we know sort of by casework that this two-way switch on the triangle doesn't have a strategy. And we can use that to say that a 6-way switch on a triangle also doesn't have a strategy because the two-way switch somehow embeds in the 6-way switch. And we can also say, again, using that information about the triangle, we can also say that, again, we know that a two-way switch doesn't have a strategy on a triangle. So that means a two-way switch also can't have a strategy on a hexagon because sort of the symmetries of the triangle somehow embed in the symmetries of the hexagon. So for getting these base cases, that's sort of the hard work. I don't have a great way of figuring out those base cases, but once you have one of these sort of simple things, you can rule out a bunch of other things, which is kind of nice.
Thanks.
Yeah.
I've got a question.
Mm-hmm.
Is there a strategy for a square with 3 switches, with each one with 3 states?
Yeah, that's a good question. So so there isn't a strategy for a square when each one has 3 states, but here's another theorem. This is nice because I can kind of scroll down and show some other related things. One thing that's kind of cool is if our switch behaves like any group at all, that is a 2 group. So it's a group of order 2 to the K. Then we have a strategy on every 2 to the L gone. Okay, so if our group behaves like choose any group of order 1024 and have our switch behave like that, sort of whatever that means, then we can come up with a strategy on a square or on an octagon or on a 16. So this is sort of one of the cooler things is that like, so I have sort of this cheeky remark, which is that 99% of isomorphism classes of groups of order less than 2000 are groups of order 2 to the 10. And there's this conjecture that almost all finite groups are 2 groups. So like sort of it's a little bit of a silly thing to say maybe, but like if this conjecture is true, then like sort of in some sense, almost all kinds of switches that you could come up with are going to work on a square and an 8-gon and a 16-gon and so on. Which is kind of fun. Yeah.
Yeah, very cool. Thanks.
Yeah.
All right, so let's go ahead and thank the speaker once more.